Welcome back to Principles Engineering. We're working on a stress strain problem, and this is problem number 9. So from our problem, I've written down some of the known things, and if you go ahead and do a quick read of your problem, it says that there's a 9,000 pound rod that's suspended from the roof of a shopping mall with a 16-foot long aluminum rod. It tells you that the modulus of elasticity in the rod is 10 times 10 to the 6th psi. Further, it tells you the maximum that the rod can stretch is 0.5 inches, and the maximum strain, the maximum stress that's allowed in the rod is 30 times 10 to the 3rd psi. So from that, what I've done is I've gone ahead and developed some unknowns. And the first unknown is the area of the rod. The second unknown, obviously, is the diameter of the rod. That's what we're trying to find. And then the third unknown is I have to convert my length into inches, and we'll talk about why here in a second. Some equations that I probably want to know and be able to use are the area of the cross-sectional area of a circle, and that is pi r squared. It is also can be equated as pi d squared divided by 4. So the last equation here is really a arranged equation that relates our stretch of the rod to the force in the rod, the original length, divided by the area, and Young's modulus. And you go, well, how the heck did he get that? So let's take a quick look and step back and pull that stress-strain relationship up. So if you actually look at your stress-strain calculation formula sheet, and I'm going to pull that up here. Just give me 1 second. And here it is. So here it is. So what you can see is I've got this relationship for the modulus of elasticity right down here. And I'll go ahead and highlight that formula that I'm talking about right there. And this is the rearranged equation. So let's do that rearranging. And let's start. And I'm going to do all of this in the light red color over here. So let's go ahead and come over into this window. And we'll do it in the light red color. So we start out with the original formula, and the original formula says that E, or the modulus of elasticity, so E says that that equals to my pressure, in this case my force, times the length original divided by the area and then the elongation delta. So what I can do is I can rearrange this, and let's go ahead and move my delta over to this side, and I'm going to do that by multiplying both sides by my delta, and you'll see what happens is it cancels out on that side of the equation, and now I'm left with the equation that my delta times E equals the force times the length original divided by the area. Now let me go ahead and divide both sides by E. And once again, you'll see they cancel out. And then what I end up with is my formula here in green, which says that my delta equals the force, L sub 0, divided by A, E. That is how we arrived at that equation. So now I'm really down to substituting and solving. So let's do that over here in white. And what I'm given, I just take my formulas, and I've got delta, and my force coming down is 9,000 pounds. My length original is 16 feet. But you know what? I kind of need to convert that into inches because my bottom factor is going to be in inches. So let me do a conversion factor that says 1 foot equals 12 inches. That will cancel out my feet units there. And then I'm going to divide this whole thing by my area, which is actually what I'm trying to find, and then my E factor, which is 10 times 10 to the 6th pounds per square inch. Now let me do one other change here from that formula. What I'm going to do now is I'm going to divide this by my delta and divide both sides by my delta. It'll cancel on that side. And I'm going to multiply both sides by my area. And that will cancel my area. So now what I end up with, again back in white, is I end up with 9,000 pounds times 16 times 12 inches divided by 10 times 10 to the 6th pounds per inch squared. And you kind of see where I'm going with this, times my elongation, which is 0.50 inches. All right, so that then equals to my area, which I just said before was pi d squared divided by 4. So let's go ahead and jam through some of these numbers. So getting my handy dandy calculator out, I've got 9,000 times 16 times 12 divided by 10 million divided by 0.5. And I come up with pi d squared equals to 3.3456. And I'm going to leave those 4 digits there until I get my final answer. So now what I can do is I can take pi d squared divided by 4 equals to 0.3456. Multiply both sides times 4. That'll cancel out. No units on this, and this is inches squared right now. And let me go back and show you why that is here. So I'm kind of hopping around, but it's late. So there I cancel pounds, pounds, inches, inches, and I'm left with 1 over inches squared, which is the same as multiplying by the reciprocal, so I end up with inches squared there. Okay, so and now what I need to do is divide by, over here, divide by pi on both sides. And my pi's cancel out. So now I'm left with d squared equals to 0.3456 times 4 divided by 3.14. So again, we'll go back and we'll use my handy dandy calculator. And I get 0.3456 times 4 divided by 3.14, close enough approximation. And I end up with something right around d squared equal to about 0.4403, somewhere in that vicinity. 0.4403 inches squared. I can come back and take the square root of both sides of my equation, and then that's going to give me my final answer, and that will be approximately 0.6635, but I'm going to go ahead and apply the precision that they ask for, 6635. So I'm going to go ahead and apply the precision, just call it 0.66. and that unit is inches. So now I've got D equals to 0.66 inches. So hopefully that helped you through the problem, and thanks for watching.